Hi everybody, welcome to the probability workshop with Sharp and S&D Technologies in conjunction with CASME in aid of the Future Fund 2.0. All right, so what have we got planned for tonight? Well, the first thing is a brief introduction, and then of course we are going to jump right into probability, and we're going to look at all of those important definitions like relative versus theoretical frequency, independent and dependent events, mutually exclusive events, Venn diagrams, tree diagrams, and counting principles. So it's quite a lot of cool stuff to cover, and I'm quite excited about this one. It was fun to create. And then, of course, I will briefly explain to you what the Future Fund 2.0 is, and then, of course, any additional resources that we can point you towards. All right, so what is probability? Probability is what people use in order to predict an event is happening. So, for example, they use it in insurance. So, if you are a gung-ho crazy person, your insurance might cost more than, say, somebody else's. If you are older and you take out life insurance, your life insurance will cost more because your risk of dying is higher and sooner, according to the stats and the probability. Okay, it's used in gambling. So when you look at the horse's odds, it's calculated by the probability of that horse winning, and that's based on a number of different factors that they look at. So all sorts of things, which are quite advanced, so we won't jump into that now. But basically, this is where you are going to use probability in real life. Okay, and then probability is about looking at the size of the chance that something might happen. So do we think a meteor is going to hit Earth tomorrow morning? No, the size of the chance of that happening is very, very small. Okay, whereas is the sun going to come up tomorrow? Yes, absolutely. So the chance of that happening is 1. Whether we can see it behind the clouds or not is a completely different story, but the sun is definitely going to rise tomorrow. Okay, so that's sort of the scale that we look at with probability. Now, tonight I'm going to be using our Sharp ELW535SA. It is a beautiful calculator. It comes in 3 different colors. It's got 422 jam-packed functions, and the Department of Education has approved it for students writing their final matric exams. So it includes an unlimited table mode, which we looked and used on Saturday, and then of course your highest common factor, your lowest common multiple, very easy to use statistics, which we will cover on Thursday nights, and of course lots of other cool things. So there are help you videos on our YouTube channel, which is Maths at Sharp. So if you want to see how to do a specific thing, there are a lot of cool little short videos that you can watch to help you with a particular function on the calculator. Cool, so the first thing that we want to look at is relative frequency. Now, relative frequency is the number of times that something actually happens during an experiment. So, for example, if we rolled a dice 10 times and we counted how many times there was a 1, how many times it was a 2, etc., that would be the relative frequency. So let's actually roll the dice. I am going to find my calculator. I hope I've actually put it up here. Okay, I'm so sorry, guys. I have not. So I'm just going to come back here. Okay, sorry. I'm just going to load this. Cool. Okay, so on your calculator, you have a random function. So you have a dice, you have a coin, you have an integer creation function. So if, for example, we want to roll the dice 10 times. So here I'm going to roll the dice. So the first roll of the dice gives me a 6. And I'm going to go back to my PowerPoint presentation, which is here. And I'm going to say we rolled it. We rolled a 6 once, right? So I'm just going to say a yes over here. And I'm going to go back to my calculator. Can you see the calculator? No. Okay, and I'm going to roll it again, and it gives us a 2. So here on the screen, we're going to write a yes by the 2. This is going to take a long time to do today. And then, of course, we're going to do another roll of the dice. So we're going to say again, and that's a 5. We're going to go back here, and we're going to say 5. Oh, sorry, yes, and so on and so forth. I'm not going to do this because I feel like we could be here all night from the looks of things. Okay, so relative frequency is how many times this thing, let's just do it 6 times, okay, just so that you have an idea of frequency here. So let me do another roll. Okay, so 1, so I'm going to come back here, and that's a yes, and then back to my calculator. I wonder if I can do it this way. Can you see my calculator now? If you can't see my calculator, just wave your hand, because this will be much quicker then. Fabulous. Okay, so we're going to roll the dice again. It's another 5. So here's another yes. And let's roll the dice again. It's another 1. So that's a yes. So how many have I got? 6. And then we're going to roll the dice again, and that's a 2. So another yes here. And again, it's a 4. This would be much faster if you were doing it with me. But anyway, and there's another 2. So how many got? 5, 6, 7, 8, 9. So one more dice. It's a 6. So, all right. So if we look at our dice rolls, okay, our relative frequency of a 1 is 2 out of 10, whereas the 2 is 3 out of 10, and the 3 we rolled 0 times out of 10. So this is our relative frequency. In other words, the exact amount of things that happened in the experiment at that particular time. Okay, now if I flipped a coin, we could do the same thing. So on my calculator, I also have a coin. So it's number 2, right? Now my coin is a math coin, so instead of heads and tails, it's going to say 0s and 1s. So if I have a coin and I press equals, I get a 0. Let's call 0s heads and 1s tails. So there's a yes, and let's do that a couple of times. So that's a yes, and then we'll do it again. So that's another one. And again, and another one. You can see sort of the pattern. Okay, so here my heads, out of 5 flips of the coin, I got 2 out of 5, and my tails, I got 3 out of 5 flips of the coin. Okay, so from this, it leads towards something called a cumulative frequency. And a cumulative frequency is just when you do a lot of experiments. So 100, you roll the dice 100 times, or you flip a coin 100 times, and so on. And obviously, the more you flip or the more you roll the dice, the more likely that your relative frequency or your cumulative frequency is going to tend towards your theoretical frequency. Now, your theoretical frequency is what you expect to get for however many rolls. So if I roll a dice, I expect to get a 1 once, and a 2 once, and a 3 once, and a 4 once, etc., etc. Okay, so I expect to get a 1 out of every 6 rolls. And I expect to get a 2, 1 out of every 6 rolls. Okay. For a coin, I expect to get a heads, 1 out of every 2 rolls, which was sort of what was happening with the calculator now anyway. Okay. So for those teachers that are listening in, what's really nice that you can do is to have your students all stand up in the classroom and to pick a number between 1 and 6 and to show you that number. Obviously, I can't do this now on a webinar, which I'm pretty sad about, but I have another game, so don't panic. And so you get your students to pick a number, and they show you their number by using their fingers. So 1, 2, 3, 4, 5, 6 on the fingers. You roll the dice using the calculator. We have a simulator that you can download off maths@sharp.co.za for free, just by the way. If you roll their number, they can stay standing. If you don't roll their number, in other words, the other 5 out of 6, they have to sit down. Okay, so that's pretty much how the game works, and you do it over a number of rolls and you see whether or not you've actually got someone left standing after a couple of rolls. And this is a really nice introduction to tree diagrams. Okay, cool. So back to everybody. Okay, so let's play the Lotto. All right, guys, what I want you to do now is in the chat function, choose any 6 numbers between 1 and 52 and type them into the chat function now. I'll give you a minute to do that. Let's see what your lottery numbers are. Don't worry, I won't use them, okay? So just pop your lottery numbers in there and then write them down somewhere that you can see. I'll give you a minute to do that. So 6 numbers between 1 and 52. Those are the lottery numbers, all right? Cool. I see one person's done it. So I'm going to pick some numbers here. I'm going to pick 18. Sorry, pardon my writing. It's terrible. 2, 7, 28. How many have I got? 3, 4. 51. Cool, guys. Are you nearly all done? I see 3 people have put their numbers in. I'm waiting for you. And 1, 2, 3, 4, 5. And my last number is going to be 3. It's the date of our wedding anniversary. Okay, cool. All right, so let's see who's got what. Awesome. Thanks, Lisa and Togozile. On the chat side of things, let's see who the Q&A is. And Tabiso, awesome. Let's see if you guys win the lottery. Okay, I see another one here. Fantastic. And thanks, Lazarus. Awesome, awesome. Okay, good choice of numbers. Right, so on the calculator, I am going to generate some Lotto numbers. Now to do this, we're going to use our random function, so second function and 7, and we're going to use the function called random integer, so that's a 3. Now here with the random integer function, you can actually choose any random digits that you would like between. Okay, so any 2 sets of numbers. So I want to generate numbers between 1 and 52. Okay, and my first number is 3. So I'm going to annotate again and I'm going to say 3. Okay, then the next number is 4. Oh, wow. We're really doing well here, guys. Okay, and then the next one is 9. Wow. Did anyone pick such low numbers? And then the next one is 13. Sorry, I haven't used the annotate function, so please forgive me for my horrendous screenwriting. And then, of course, 32. And the last one is 52. How ironic. Okay, did anyone get at least one of these numbers? Let's see. Okay, so on my side, I think I got the 3, but I don't think I got anything else. Let's see. Tabiso, you got a 9. Okay, you picked 9 twice, by the way. And let's see on this side. So we've got 28, 8, 7, 50, 17, and 12. None for Lisa. Tokozile, none for you either. And Lazarus, you got the 32. Nice. And that's all. Oh dear. So none of us won the lottery tonight. Whoops. Okay, cool. So you can see it's quite a nice fun game to play. So how does the lottery work and why did we do that exercise? Well, let's work out the odds of you actually winning the lottery. Okay, so the chance of you getting one number right is 1 out of 52 different options, right? But once you remove that ball, how many options do you have left? You have 51 options, right? So the chance of getting a second number in a row correct is 1 out of 51. right? And so on and so forth. So what we would do is we'd multiply all of these together 6 times. So we'd have 1 out of 52 times 1 out of 51 times 1 out of 50 times 1 out of 49 times 1 out of 48 times 1 out of 47. All right. We're all happy with that. And I think this is something that we should definitely calculate. So I'm going to pull out my calculator. So it is 1 out of 52 times 1 out of 51 times 1 out of 50, so that's 3, times 1 out of 49 times 1 out of 48. So how many have we got? 1, 2, 3, 4, 5, last one, and times 1 out of 47. Okay, does anyone want to hazard a guess? Do you want to let us know what you think your odds of winning? Is it 1 in a million? Is it 1 in 10 million? Is it 1 in 100? In which case, why haven't I won the lottery yet? Is it 1 in 20,000? Anyone want to jump in? I'll give you a second. No thoughts. Okay, cool. All right, so let's see what it is. It is, wow, a big number. So basically 6.8 times 10 to the power of negative 11. Okay, so 11 zeros, which means it's 1 out of a billion is 9 zeros. So it's 1 or 6.8 out of 100 billion. Does that sound like good odds? I don't know about you, but I don't think so. And yet I still wind up playing the lottery because, you know, you always hope and you always hear about people winning. So there's no judgment here if you are playing the lottery. Cool. All right. So independent and dependent events. Now, an independent event is an event that has no effect on another event. Okay, so from one roll of the dice to one coin toss, it has no effect on the next roll or the next coin toss. Okay, however, when we looked at pulling out the lottery balls, because we weren't replacing the balls back into the container where those were popping out of, that is a dependent event. In other words, your odds and your probability changes because it depends on the previous event. Okay, so that's the difference between independent and dependent events. I know someone asked about that on the reply slip, so cool. So don't worry about that. That is a chemistry formula. I was just being facetious, to be totally honest with you. Okay, so what it has is an effect on your formulas. Now, when something is independent, the probability of A and B happening is the probability of A times the probability of B. And the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, and I want to show you this here because this is where that formula comes from. So where there is an overlap, you can see there was a yellow circle and there is a blue circle and it overlaps to make green. But that area is counted twice, once for the probability of A and once for the probability of B. So when you have the probability of A or B, you need to cut out that area once. Okay, and that's where the probability of A and B come in. So that's A and. This little upside down U means and, by the way. And then if you have mutually exclusive events, it means that only one of those events can happen. So you can either wear slops or you can wear tackies, but you cannot wear both. Okay, at the same time. I was trying to think of a better example, but my brain was tired this morning. But yes, so you can only do one out of however many options there are. You cannot choose two. Okay, so if, for example, you cannot study both a medicine degree and a counting degree, because that would be at the same time. Okay. You can do it concurrently or after each other, but you cannot do them together because it would be far too much work. Just word to the y's. And then also note here that the probability of A and B happening is 0, and that's what makes it mutually exclusive. Okay. I was trying to think of a dating example, but none spring to mind. Okay, so let's look at some of these examples. So given the probabilities below, say whether events X and Y are mutually exclusive, independent, or neither mutually exclusive nor independent. Okay, so when we are looking for a mutually exclusive event, we are looking for the point where the probability of A and B, or in this case, X and Y, are 0. Okay, so I can only see an and that's not 0. And here's not 0. So those B and D are not mutually exclusive. Okay. Here at A, that is also not a 0. C is not a 0. So the only mutually exclusive event is actually the probability of X and the probability of Y. Okay, now if they are independent, it means the probability of A plus the probability of B. No. Sorry, I'm going to go back to my formula here. The probability of A and B are multiplied, and that will give us the probability of A and B. Okay, so if we go look, 0,4 times 0,1 should give us 0,04, which it does. So this option A is independent. Okay, in other words, they don't rely on each other. Let's look at this one. We have the probability of X times the probability of Y, and that should give us 2 times 7 is 14, so it would be 0,14. And here we can see that that is not the case, so this is actually a dependent event. Okay, so these would be dependent over here. Then we have 6 times 2, which gives us 0,12, and that is the probability of X and Y. So we know that C is an independent event. And then we have 3 times 8, which is 24, and you can see neither of these are 24. So that means it is neither mutually exclusive nor is it independent. It is a dependent event. Okay. And then lastly, we have 0,5 times 0,4, which should give us 0,2, but we already discussed that this is a mutually exclusive event, and so we don't have that, we don't have an independent event either. Okay, so it's dependent. Well, not, it's actually not dependent either, but there you go. Okay, all happy? Cool, let's move on to Venn diagrams. Right, so this is a Venn diagram. Well, it's actually just a bunch of circles that look like a Venn diagram. But basically, Venn diagrams are used to represent events within a sample space. So you can say event A is prime numbers, event B is multiples of 10, and event C is pink flowers. Okay, and then you have to look at what crosses over. So where is it A and B? It would be this overlap here. Where is it A and C? It's this overlap here. And B and C is this overlap here. And then, of course, that very middle lap would be A, B, and C. So let's start with the more basic one. So I've got the numbers between 1 and 15, and I have 2 events. Event A is that these numbers are a multiple of 3, and event B is a multiple of 5. So if we go through them very quickly, I'll show you the answer after this. Is 1 a multiple of 3 or 5? No, it's not. So it actually goes outside of the space in the square outside. Okay, 2 again, also outside the space. 3 is a multiple of 3, but not a multiple of 5. So it goes in this part of A's circle. 4, neither a multiple of 3 or 5. 5 is just a multiple of 5. So here, I'm going to put it on this side of the circle, so that doesn't overlap with circle A. 6 is a multiple of 3, but not a multiple of 5, so it goes just in this side of the A. 7 is a neither, so it goes outside. 8, again, neither, so it stays outside. 9 is a multiple of 3, but not of 5, so it's just in the A part of the circle. 10 is a multiple of 5, but not a multiple of 3, so it stays on this side of the B circle. 11 is a prime number, so it doesn't belong in either circle, and we leave it on the outside. And then, of course, 12 is a multiple of 3, but not of 5, so it goes in the A part of the circle. 13 is a prime number, so it doesn't work with either, and it lives outside of the two circles. 14 is a multiple of neither, again, so it lives outside the circle, and 15 is a multiple of both. So in fact, it is the only number that lives inside of this overlap between A and B in the dark blue. Okay, so there we can see all of the answers. Is everyone happy with that? So Lisa's asked, when would we use the formula of probability of A or B equal to the probability of A plus the probability of B minus, so Lisa, in fact, it's right here. So when we are doing a Venn diagram, and I'll show you another example just now with rugby, we will use that exact formula. So give me a sec here, I'm going to get to that point in a few. Okay. So sorry, my Venn diagram got all skew and bunched in the corner. What we did is we added a third circle called prime numbers. Now, prime numbers, as we can see, are 1, 2. The 3 is a prime number, but it also belongs in the multiples of 3. So it is that overlap between A and C. Then 4 is a multiple of 2, so it doesn't belong in any of these. 5 is a prime number, but it is also a multiple of 5, so it belongs in the overlap between C and B. Then 6 is a multiple of 3 only. 7 is a prime number, so that belongs in C. 8 is none of the above, so it goes in the space outside of the Venn diagram. Okay, so this is just a very nice way of breaking down what's going on with the Venn diagram, okay, and how these things are calculated. Okay, so let's look at a question. This question was taken from the grade 11 handbook and study guide written by Kevin Smith. Fantastic textbook. If you are struggling, it's got lots of nice examples. All of the examples are fully worked out, so it's a really nice study guide slash textbook if you're looking for a little extra help. Okay. So the question says, in a survey, a group of grade 11 learners were asked if they play rugby or soccer or both. Okay, the Venn diagram on the right shows the results of the survey. So we can see this circle is for rugby, this circle is for soccer, and this box is all of the grade 11 students that were surveyed. Okay, so if we look, we need to know how many students in total were asked, do you play rugby or soccer? So that is just a simple question of adding all of these values up. So we have 100 plus 70 is 170 plus 150. So 270 to 320, right? Plus 180 is 420 plus 80 is 500. So in total, there were 500 grade 11s that were asked. Now it says, determine the probability that a learner chosen at random from the group plays rugby, but not soccer. So that's this part of the rugby circle, okay? It excludes the point where they play soccer as well. So it's just 100 out of the total group of students, which is 500. The next one, so your probability is 100 out of 500 or 1 out of 5, okay, 20%. The next one says, does not play either sport. So these students are all excluded, and we just look at the 180 over 500, okay. The next one says, plays soccer. So here we need to include both the 150 and the 70. So we're going to add the two of these together, which gives us 220 out of 500. Okay, and then plays both sports. So here is where we would use that probability of A or B. okay? So we have the probability of A is 100 plus 70, which is 170 over 500, plus the probability of B, which is 220 over 500, minus the probability of, sorry, I've lost my mouse here, the probability of A and B, or the rugby and soccer, which is 70 over 500. So Lisa, that is exactly where we would use that formula. Okay. Are there any questions here? Are we all good? We're happy? No problem, Lisa. It's a pleasure. All right, sweetos, let's move on then. So the next thing that we want to look at is tree diagrams, okay? So I didn't actually draw this tree diagram myself, but it is a nice example of choosing between red and blue, okay? So basically a tree diagram helps you to calculate the probability of several events happening together. Now we can look at a favorite example in most question papers is marbles, okay? So I have 4 marbles. 2 are red, 1 is blue, 1 is green. What are the chances of you pulling out a red marble? It's 2 out of 4. The chances of you pulling out a blue marble is 1 out of 4, and the chances of a green marble is 1 out of 4. And then if I did it in a row, when I replace the marble and if I don't replace the marble, I'm going to get to that in a second. I hope. No? Okay. So here, it's actually why I made this point here. So you can see how independent, dependent, and mutually exclusive events affect your probability. So for an independent event, you would put the marble back in the bag, and your probabilities of the red marble would stay the same throughout your tree diagram, no matter how many times you take a marble out, because you are taking a marble out, and once you're done and you made a note of your result, you are putting it back in the bag. Whereas a dependent result would mean that you are taking a marble out of the bag and you are leaving it outside of the bag. And so when you do your probability or your tree diagram, your probability changes. So that's the difference between an independent and a dependent. We're going to look at an example in a sec. Okay, I see there's a question. I'm just going to chat there. Oh, Shane, I'm sorry to hear about your network issues. Don't worry, we'll send you a recording. Okay. So a certain bag contains 4 red marbles, I told you, and 12 blue marbles. Okay, so what is the probability of selecting a red marble from the bag, and what is the probability of selecting a blue marble out of the bag? So red, the chance would be 4 out of a total of 4 plus 12, which is 16. Sorry, guys. I haven't had enough coffee today, okay? So it would be 4 out of 16 or 1 out of 4 if you simplify your fraction. And the probability of choosing a blue one would be 12 out of 16, the total number of marbles that you're looking at. Okay, so those are your 2. And of course, if we simplified that fraction, which they do expect you to do, and you can do on the calculator, so don't panic. Let me show you quickly. So on the calculator, let's just press on. If I had 12 out of 16, I could just say 12 out of 16 equals, and it shows me that it's 3/4. If I want it as a decimal, depending on what they ask you for, that's not normally specified, so leave it as a fraction for the most part, okay? So your decimal would be 0.75. Okay, so that's the 2 ways to write probability. Okay, so our first example, or our next part of this question says, if 3 marbles are taken out of the bag and not put back into the bag after the draw, what kind of event is this? This is a dependent event. It means your probabilities are going to change as you draw your tree diagram. So if we look, it says, the first question says, draw a tree diagram. So I've done that for you. This is actually from a worksheet that Maths at Sharp has on the website. So when I send you a link to the video recording, I will send you, you can just email me and ask me for the worksheet, and I will send you the grade 11 worksheet, which is where most of these examples come from. There is a grade 12 fundamental counting principles worksheet as well, if any of you are in grade 12. Okay, so just ask me, please can I have the grade 11 or the grade 12 worksheets, and I'll send you the worksheet and the memo. Okay, because you know, practice is key. Okay, so the first thing is to draw a tree diagram. So I've done a very basic one here. You've got your red and you've got your blue, and we already worked out the probability of taking 4. Your chances of getting a red are 4 out of 16, and your chances of getting a blue are 12 out of 16. Okay, so I'm just going to annotate here so you can see what I mean. Oh, this is even better. Okay, so 12 out of 16 and 4 out of 16. So now, because we've taken a red one out of the bag, we now have 3 red marbles left out of a total of 15 marbles and not 16 marbles. Just remember that, okay? But the blue, there are still 12 marbles left out of a total of 15 marbles. Now, if I take another red one out of the bag, now there are only 2 red marbles left out of a total of 14 marbles, whereas there are still 12 marbles left out of a total of 14 marbles. So you can see exactly how your probability changes depending on whether your event is dependent or independent. Okay, so keep that in mind. If they do not replace, it is a dependent event, and it means your probability changes. If they do put the stuff back, or they do with replacement as the terminology, then your probabilities will stay the same, and I'll show you that in the next example. Okay, so the next question says, what is the probability of only choosing red marbles on all 3 draws? So if we look, we've got red, red, red. And when you're doing all 3 in a row, you are multiplying your probabilities together. Okay, so the probability of me getting all 3 red is 4 out of 16 times 3 out of 15 times 2 out of 14 is 1 out of 140 different options. Okay, so it is the rarest combination that you can get from the looks of things. Okay, what is the probability of selecting 1 red and 2 blue? So now if we go through our table, I suggest when you do your tree diagram to just write down the different combinations. So follow your thing. So if I follow my tree, it's red, then it's red, then it's red, and I have a red. If I follow this one, it's red, and it's red, and then it's blue. So that's the next option. It's red, then it's blue, then it's red, so that's this one here. It's red, then it's blue, so it's this one here. Okay, so we are looking for, the question says choosing 1 red and 2 blues. So I'm going to go back to my pen. Sorry, guys. Do this because haha. Okay, so we're looking for 1 red and 2 blues. So red, red, red is not what we're looking for. Red, red, blue, no. Red, blue, red, no. Here's 1. Okay, and then blue, red, red, no. And then blue, red, blue, yes. Blue, blue, red, yes, and no. So I've got 3 different possible combinations or 3 different ways that I could get that combination of marbles. So here it is 11 out of 70, 11 out of 70, and 11 out of 70, strangely enough. Now, when you're going down and you're counting how many different ways that you can get this thing, you are going to add these probabilities. So here I'm going to have 11 out of 70 plus 11 out of 70 plus 11 out of 70. So I know 11 plus 11 is 22, plus 11 is 33. So the probability of selecting 1 red and 2 blues is 33 out of 70, or in fact, almost very, very close to half. Okay, so it's pretty common. Okay. The last question says, what is the probability of selecting a green marble? And this is a trick question because there are no green marbles in the bag, which means that there are 0 green marbles. And so your probability of getting a green one is 0. Okay. Then, of course, oh, sorry, guys, you don't want to see that. That was an accident. Let's look at the next one. So now the next one says, if a marble is taken out of the bag, sorry, I just need to clear away this annotation, otherwise you're gonna, it's gonna confuse you. Okay, so, right, so here it says, if the marble is taken out of the bag and then put back into the bag after each withdrawal, in other words, it is an independent event, okay? Taking one out does not affect the next draw. Okay, so in other words, I have 4 red marbles in the bag and I take one out, but I still have 4 red marbles in the bag when I do my next draw because I put it back again, and I still have 4 red marbles again because I put it back again. Okay, so that's the difference between the two. So again, draw a tree diagram and you can see your probabilities stay exactly the same throughout your tree because they are not being affected by the previous draw. That's basically it. Okay. Now it says, what is the probability of choosing a 3 blue marbles in a row? So here we can see it is this bottom tree line here. It's the BBB. Okay. And we look at our probability, which is 12 out of 16 times 12 out of 16 times 12 out of 16. And this has been simplified to 27 out of 64. Okay, the next one says, what is the probability of choosing 2 red marbles and 1 blue marble in any order? Sorry, I just want to erase this. So here we have 2 red marbles and 1 blue marble. So we're looking for red, red, blue. Okay, so red, red, blue. Red, blue, red, it doesn't matter about the order. Not that one and not that one. So we need 2 reds and 1 blue. So there's another one, and no, no, no. And again, when you're going down, you add your probabilities. So we're going to have 3 out of 64 plus 3 out of 64 plus 3 out of 64. So that is 9 out of 64. Okay. Then the next question says, what is the probability of choosing at most 1 red marble? In other words, only 1 red marble or 0 red marbles. So no, that one doesn't count, that one doesn't count, that one doesn't count. 1 red, so that one does. No, that one's got 2 reds. That one does, and that one does as well. So now we're going to add 9 out of 64 plus 9 out of 64 plus 9 out of 64 is 27 out of 64 plus 27 out of 64 is 54 out of 64. So your odds of choosing at most 1 red marble is 54 out of 64, which is actually a really high probability. And of course that is skewed because you have 12 blue marbles versus only 4 red ones. So it will be quite a common thing. Okay, oh sorry, let me just erase here before we go on to the next set of notes. Alrighty, so let's talk about the fundamental counting principle. So if order doesn't, and this is permutations and combinations, okay? So if order doesn't matter, it is a combination. You're chucking everything into a bag. You are combining it. So like a cake, it doesn't matter in what, maybe a cake's a bad example, pancakes. You chuck all the ingredients in for the pancake, you stir it all up and you throw it in the pan. It doesn't matter in which order you put the ingredients in. Okay, whereas a permutation does matter. The order does matter. So that is the different way that elements are lined up. Okay, so if, for example, we had a race and you had to choose the top 3 kids, you could have either Susie, Johnny, or Billy Susie, Johnny, or Billy, Johnny, Susie, and so on and so forth. So you have a lot more different options here in permutations than you do with a combination. Okay, so again, a typical combination question would be with a license plate number, for example. Okay, so for each of the stories below, say whether it is a permutation or a combination. So 200 students who enter a competition to win a prize. That would be a combination because it's not telling you that there is any specific order in which the students will be picked. 200 students, 10 of whom are chosen as volunteers. Again, that is a combination. The order of your volunteers doesn't matter. 7 children who run away a race, that would be a permutation because the order that the children come in the race would change, and that's the difference, okay? And then 10 cars entered in for car of the year. Well, if you rank the cars, it is a permutation, but if it's just a global top 10 and there's no specific order, then it would be a combination. And then lastly, a sample of 100 random people selected from your neighborhood for a survey. That again is a combination. There's no particular order in which it is done. I see there's a question here. Oh, thank you. Yes, but we will try and get through it and give me a shout if you have questions. Alrighty. So let's go through, so how to do a permutation on your calculator. What you're going to do is we're going to go here. So say, for example, we have 4 different things and we want to choose 3 of them and put them into a specific order. How many different ways can we order those 4 things into 3 different special places? Okay, so we have 4, then we use our orange button and we use number 6. You'll see above it in orange it says NPR, so it even tells you the order in which to write these things. So N is your total number of objects that you have, or people, or whatever the story is about, and then your R is the number of spaces available for them to fill. Okay, so if we put in 3 and we say equals, there are 24 different ways to line up these 4 different peoples into 3 different slots. Okay, now let's look at a combination. So I have 4 people, I have 3 different slots. Again, second function, you'll see NCR, or number combination number of slots is on 5, and then I have 3 different slots, so I say equals, and there's only 4 different ways to do that because it doesn't matter in which order it is, so it narrows the amount of options that you have quite dramatically. Okay, so that's just combinations and permutations. So here's a very fun example. We're given the word prestidigitation, which is a very fancy word which means sleight of hand or quick fingers. It's what the magicians use to make magic look magic, okay? So it says, how many ways can the letters in the words prestidigitation, I should have picked an easier word, right? Be arranged. And that's just using your factorial function. So we count how many letters there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is a lot. Okay, so you have 16 different letters, and we're just talking about arranging them in 16 in all higgledy-piggledy ways. So we say 16 and we say factorial. Okay, so that's the answer to that sort of type of question. Massive. So it's 2,09 times 10 to the power of 13. Remember, your chances of winning the lottery were less than this, had a smaller amount. So you can see just how many times 16 different options makes a difference. Okay, so let's look at your next question. Your next question says, how many 6-letter words can be made using all of the letters above? So that is a permutation because you have different words, okay? So we're going to use our permutation. So we have 16 different options, right? Then we use our permutation button and we have 6 different spaces for them. So we have 5,765,760 different ways to arrange the 16 letters in prestidigitation into 6-letter words. Okay, so you can see why probability is so much fun. Okay, then the next one says how many 6-letter words can be made if there are no repeated words. Okay, so now of course the problem is we have lots of I's and we have lots of T's, so we need to remove that from our setup. Okay, so we're going to take the 5 million that we found over here and we're going to subtract the different options of those T's. So I have 1, 2, 3 T's and 1, 2, 3, 4 I's. Okay, so on the calculator, I'm going to take this answer and I'm going to say minus, it was 3 T's, right? So that's a factorial, times 4 I's with a factorial, and that gives us 5,765,616 different words. Okay. Sorry, let me just switch over here and close my annotation. So, if 5 letters are randomly selected from the word above, how many ways can the letters be chosen? Again, this is a combination. So we're going to use our calculator and we're going to say we have 16 letters, second function, and we're using a combination because order doesn't matter, and 5 and equals. So you can see it's quite a sizable difference here. You've only got 4,368 different ways to pick 5 letters and put them in a group. Okay. Then the last, sorry guys, I didn't mean to do that. The last thing is, what is the chance of getting the word tastier from prestidigitation? Now, tastier is 1, 2, 3, 4, 5, 6, 7 letters. And it's 1 out of, so sorry, my bad. So the chance of getting the word tastier from prestidigitation is 1, 2, 3, 4, 5, 6, 7 letters out of 16. Okay, and it's a single. So it's a particular order. In other words, it's a permutation. So we have 16, second function, and P for permutation, 7 different letters equals. So it's the chances of getting the word tastier is 1 out of 57,657,600. Okay, so that you can see why having so many options makes it, and that's why they use letters in number plates, just as a side note. Carl, your question is, are the different say I's distinguishable? Oh, for this question. So yes, in this sense, we could have 4 I's in a row together. Okay, I understand what your question is. Yeah. So Tokozile says, when would we use a factorial? So a factorial is when we look at the whole group and how many different ways we can arrange them. So if, for example, I picked 4 students and I looked at how many different ways I could put those students into order, okay? So in the first place, I have 4 different options, okay? In my second place, I have 3 students left, so I have 3 different options, okay? In my third place, I only have 2 students left. Okay, so that's 2. And in my last place, I only have 1 student left. So I have 4 times 3 times 2 times 1. And that is the definition of a factorial. So we would use a factorial when we are looking at filling a space with a set number of people or things. So for this first question, how many ways can the letters in the word prestidigitation be arranged? That is a factorial question because we're looking at all of the letters, the 16, and we're filling all 16 spaces in different ways. So again, let me just do it on the calculator as a reminder. So I can do 16 second function, and it's on number 4. That little N with the exclamation point, it's not shouting at you, it's saying it's a factorial. That's the maths notation for that, and equals. And remember, we came up with that massive, massive number. If I did it with 4, though, you'll see it's a much smaller number because it's 4 times 3 times 2 times 1. Okay, so 4 times 3 times 2 times 1 gives us exactly the same answer. Okay, and that is the definition of a factorial. So a factorial is including all of your options in all of your space, if that makes sense. Okay, awesome. I think there's one more example. So, thanks, Tokozile. Okay, so you have invited 12 people to dinner and they are seated around a beautiful table with the fairy lights and everything. Don't do this now in Corona, just FYI. So if there are 7 ladies and they are seated next to each other, how many different ways can the ladies be seated? And this is exactly where we would use a factorial. So again, let's just do it quickly on the calculator because I can't brain that in my head. So 7 factorial means that there are 5,040 different ways that these ladies can sit next to each other. Doesn't that blow your mind? And that's why planning a wedding is so difficult. Okay, so if the guests randomly draw their seat number from a hat, how many possible ways can all the guests sit around the table? And again, that's a different, that's a factorial. So it's just a factorial with 12. So we have 12, and then we have, no, I'm sorry, I'm lying to you. No, it's a factorial. So there we go. So it would just be 12, which is 479,001,600 ways that they could sit around the table if they picked random numbers. Okay. The next question says, after dinner, the party separates to go home and breaks into groups of 4, each traveling in a different direction. How many different ways can the dinner guests be grouped? So here, I have to think about this one now. So you have 12 different guests and there are 4 different groups. Your order doesn't matter, so it's a combination, and 4. So there are 495 different ways to put these groups together with the 12 different people. Okay, making sense so far. The dinner party is a dress-up party and prizes are awarded to the first, second, and third best dressed. How many possible ways are there for the prizes to be given out? So this one is a permutation because order does matter. So on the calculator, we have 12 guests and it is a permutation and there are 3 spaces to fill, first, second, and third, and equals. And so there are 1,320 ways for the different guests to win the prize. Okay, mind-blowing, isn't it? When you think about odds like this. If the top 3 best dressed are chosen, but it doesn't matter who is first, second, or third, how many different ways can the top 3 be chosen? So this now is telling you that it is a combination. Okay, so we have 12 guests, it is a combination, and there are 3 spaces. So it is 220. And can you see the massive difference between how many permutations where order does matter versus how many combinations when order doesn't matter? Okay, and that's really, if you cannot remember in the exam, do this. So take the same number of people and the same number of spaces and look, and then you can see when the order matters, I should have lots more options. When the order doesn't matter, I should have much less options. And that's the difference between a permutation and a combination. All right, cool. So that is everything on probability for tonight. It is an hour in. I think I did it pretty accurately. Are there any questions? No. I'll just give it a sec while I drink my cold coffee. Anybody? No. Okay, great. Fantastic. So before I end off, I just want to tell you a little bit about Future Fund 2.0. I do see a question. Haha, how exciting. Okay, yes, Tokozile, I'll tell you in a second, okay. Right, so for Future Fund 2.0, basically what we are trying to do is raise money to help students who cannot afford their own calculators to get calculators. We are doing it in conjunction with CASME, which is an NGO based in Durban. Okay, so if you know some rich uncles, not hint, hint, wink, wink. You can't see my face, I'm winking. And they need a tax break. This is a great opportunity to help students who need the help and don't have access to a lot of resources, as well as get a tax break. So for every 200 Rand you donate, these students will be getting a fantastic scientific calculator to help them write their matric finals and actually try and improve their results. Now, I did some research, and in a matric paper, if you don't have a calculator and you don't know how to use it, you can lose out on 25% of your marks. That's a huge difference. That's the difference between a B and an A, or a C and an A for that matter, or passing and failing. So it's a really important and critical thing for all students to have, and that's something that we are working towards at SHARP. Okay, now, for those of you who missed out on the previous workshops that we did and you want to watch them, you can go visit our YouTube channel, which is maths at symbol sharp.co, but maths at sharp. If you search it on YouTube, it's a specific channel, and then you should get all of the links there. Otherwise, you can just mail me and ask me, and I'll happily send you the links to the specific videos. We've done quite a few now. So there's the functions video, there's a trigonometry video from last week. We did financial maths on Saturday. We're doing probability tonight, and then on Thursday night is stats. So join us for that one. It's going to be lots of fun. And then, of course, guys, if you are looking for worksheets, remember that you can download free worksheets and exam papers from maths@sharp.co.za. So teachers, block your ears for a second. Students, you are welcome to register as a maths teacher. It is cool. Okay, we're happy for you to do that. There's no screen test. It is free. So just register as a teacher and download whatever you want. Otherwise, you are welcome to contact me through the student question or the contact page, whatever floats your boat. And you can download, or I'll send you the worksheets. Okay. Don't go yet. I just want to stop the YouTube channel recording. For those of you who are watching on YouTube, thank you so much for joining us. Please watch our other videos and please support us on the Future Fund 2.0.